Hello again, everyone. In this video, I want to get a little more quantitative detail about the relationship between the heat capacity at constant volume and the heat capacity at constant pressure. So previously, what we've talked about is we've mentioned that the specific heat of a substance depends on how you add the heat, right? So if I add 10 joules of heat to something, its temperature will go up by some amount. But that amount that it goes up will depend on the conditions under which the heat is added. The main equation to think about here is something that I wrote like this: dq at constant x. So I'm adding a small amount of heat, keeping x constant. And x is like, it's a placeholder for some state variable. It could be pressure, it could be volume, it could be something else. So it's just like, I'm adding the heat, holding x fixed. I'm going to be able to write an equation that looks like this: something times dt plus something else times dx. Again, x is a state variable. So if I'm adding the heat keeping x fixed, then dx is equal to 0 if x is fixed. When I add the heat dq, the temperature goes up by some amount dt, and how much it goes up depends on what's in front here. And that is what we call the specific heat, the molar specific heat at constant x. Okay. We also argued previously that the molar specific heat at constant pressure is larger than the molar specific heat at constant volume for an ideal gas. And that was because if I took a cylinder of ideal gas and I added heat to it, if it's under constant pressure, the cylinder will expand and it will do work. So some of the energy that I put in the form of heat will be used up by the gas doing work on the environment. Whereas if I keep the volume constant, I don't let the gas expand, then I'm adding the heat at constant volume. The gas can't do any work, so all of the energy that I put in will go into the temperature increase in the gas. So we know, just based on that argument, that CMP is bigger than CMV. But how much bigger? That's basically what I want to get to today. The last ingredient that we're going to need is, I claimed to you, but I didn't really prove it rigorously, we'll come back to it, that the internal energy of an ideal gas depends only on the temperature. It does not depend on the volume. So U, for an ideal gas, depends only on the temperature, and it's equal to the number of moles times CMV times T. So what we're after is a relationship between CMP and CMV for an ideal gas. That relationship is called Mayer's equation, and that's what we're going to try to derive. So we can start with the first law of thermodynamics, which looks like this: du is equal to dq minus dw. And then in a reversible process, the work done is p dv, dq minus p times dv. Just like that. Sorry, my u's and my v's are looking a little too similar here, so that's du. Okay, now let me divide everything by the number of moles. So I'm going to divide both sides by the number of moles. And then on this side I get du. Number of moles is constant, we're assuming it's a fixed container. It just changes the capital letters to small letters, right? Minus p times dv, like this. Okay, so U is the specific internal energy, Q is the heat added per mole, and dv is the change in the specific volume. Okay, now let me rewrite this as dq is equal to du plus pdv. Let's think in general. U could be a function of T and V. Now, you know it for an ideal gas, in fact, it's a function of just T, but let's just take a more general situation first. So that means that du can be written as an exact differential, du dt at constant V plus, times dt, plus du dv at constant t dv. And then I substitute this equation in here. Okay. So let's do some algebra, clean it up a little bit. dq is equal to, putting everything in here, du dt at constant v dt plus du dv at constant t dv plus pdv. And then I'm going to group these two terms together, those last two terms. So du dt at constant v dt plus this whole thing, du dv at constant t plus p dv. Whoops, dv is on the outside. Okay. Now, compare this with the equation that I mentioned at the very beginning. Remember, if you ever see an equation that looks like this, dq is equal to something times dt plus some other thing times d of some other state variable. Then the thing in front of the dt is the specific heat when x is fixed. All right. So I'm comparing this now, what I just wrote, compare with. So compare this with dq is equal to cmv dt plus something times dv. Okay. So in other words, if the volume is fixed, dv is equal to 0, and then if I add some amount of heat and the temperature change goes up by some amount dt, the thing that relates those two is cmv. So by comparing this equation with the one above it, I can see that the coefficient in front of dt is cmv, so that means this must be cmv. And I don't really need this other thing, but what, you know, this term is equal to this term, but that is not really relevant for us. So this was the argument we used to derive that cmv was du dt at constant v. In general, this is really not just for an ideal gas, this is generally true. Now what I want to do is determine CMP. So my goal here is to determine the molar specific heat CMP at constant pressure. So to do this, I need an equation that looks like this. dq is equal to something times dt plus something else times dp, right? That means that if I add the heat with constant pressure, whatever goes here will be CMP. Okay? In other words, this variable here has to match this variable here. So that's what I'm after. I need to write an equation that looks like that. Let me start with this equation here. Okay, so we'll start with this one and try to play with it and get it into the form that we need. So let me rewrite this again. dq equals this partial derivative, du dt at constant v, but that is equal to cmv according to this equation here. So I'll just write cmv dt plus, and then I've got this other term, which is du dv at constant t plus p. du dv at constant t plus p. And this is all times dv. Okay. Now, this is generally true. Now I need to specify to the ideal gas. So let's specify to an ideal gas. An ideal gas, U is a function of T only. Doesn't depend on the volume. So that means this is 0. So the energy of the ideal gas doesn't depend on the volume. Okay. So now I've got dq is equal to cmv dt plus p dv for an ideal gas. And what I'm after is an equation which looks like this one up here. So what I need to do is I need to get rid of dV in favor of dP. So I need to use now the ideal gas equation of state, which is P times V equals R times T. You might be thinking, wait a second, isn't it PV equals nRT? This is a small v. Remember, P capital V is NMRT. If I bring the NM to the other side, this is PV over number of moles equals R times T, but this is the small v, right? PV equals RT. So if I deal with the specific volume, I don't need to write the number of moles there. Okay. Let's take the differential of both sides. dPV equals dRT. And the left side I have a product rule, PdV plus VdP. And the right side, the R is a constant, so I just have R dt. Okay. Now let's, let me rewrite this a little bit. PdV is equal to R dt minus V dP. And I'm going to take this and substitute it in above. So this whole thing, I'm going to substitute in here. Okay. So let me rewrite it again. dq is equal to CmV dt plus PdV. But PdV is R dt minus VdP. So plus R dt minus V dP. Now let's group it together. dq CmV plus R times dt. So grouping the terms which are proportional to dt minus V dP. Okay. Now compare that with the equation we were after. So let me just grab this one. So compare with this. So I've been able to write an equation which looks like dq something times dt plus something else times dp. And that means that whatever's in front of the dt is the molar specific heat when this other variable is held fixed. So that means that CmP is CmV plus R. So what we've been able to derive here is what's called Mayer's equation. CmV, molar specific heat at constant volume, plus R is equal to CmP. So we know that the specific heat at constant pressure is bigger than the specific heat at constant volume, but by how much? The difference is R, so one of them is bigger than the other by an amount R. That was what we were trying to derive in this lecture. Let me summarize with a handy table for ideal gases. So, handy summary for ideal gases. We had two kinds. We have monoatomic and diatomic gases. So monoatomic was like helium, argon, krypton, the ones that just have one atom. And the diatomic are the ones like N2, 2 atoms of nitrogen in a gas molecule, O2, H2, so on. CmV is 3/2 R for this. You can measure it experimentally. Okay, I haven't derived it for you, but I've claimed that if you add a known amount of heat to a gas and you measure its temperature change, you can measure its specific heat. And for a monoatomic gas, it's 3/2 R. For a diatomic gas, it's 5/2 R. And what is CmP? Well, we know that I just add R to it. So 3/2 R plus R by Mayer's equation, that's 5/2 R. And here CmP is 5/2 R plus R, which is 7/2 R. Okay. Finally, there's a handy combination of constants which shows up a lot. and it's called gamma. It's the ratio of CMP divided by CMV. You know it's got to be bigger than 1 because we know that CMP is bigger than CMV. It's called the Adiabatic Index. You can figure out what it is for a monatomic gas and for a diatomic gas. So for monatomic gas, what is gamma? It's CMP over CMV. It's 5/2 R divided by 3/2 R, which is 5/3. And for a diatomic gas, it's 7/2 R divided by 5/2 R, which is 7/5. So there's a nice, useful table for you when you're solving. You need to reference ideal gas specific heats. Depends on whether the gas is monoatomic or diatomic, and all of the information you need is in this table. So we will use a lot of these going forward. Let me briefly summarize. So in this pre-lecture video, we used a couple different things. We used the first law of thermodynamics. We used differentials for du to write equations which look like dq is equal to something times dt plus something else times another state variable. And I was able to use this to read off what is the specific heat under these particular conditions. So if the volume is fixed, the molar specific heat is du dt at constant V. I specified to an ideal gas, so an ideal gas, I could cross off this term. It's more complicated if it's not an ideal gas. I cross off this term, and then I use the ideal gas equation of state, PV equals RT, to write another equation, which is dq equals something times dt plus something times dp, and I was able to read off the molar specific heat at constant pressure. And that gave us our main result, which was Mayer's equation. CMP is bigger than CMV by an amount R. Then I made this table which lists CMV, CMP, and gamma, which is the ratio of those two for monoatomic gases and diatomic gases. So I hope you found this useful. We'll go a little bit deeper to this in class, and in particular, I'll try to prove some of these other things, like why does U only depend on T for an ideal gas? That's something that we'll discuss in class. And we'll start using this adiabatic index when we start talking about adiabatic processes. Thanks again for your attention. See you all in class. Bye for now.